My conceptual question for IQE8 is an engineer predicts that an inlet stagnation temperature of 50 kPa and an inlet stagnation temperature of 25 degrees Celsius will produce an exit stagnation pressure of 700 kPa. However, the actual pressure comes out to 900 kPa. How does the increased pressure at the exit affect the work calculation? An increased stagnation pressure increases the pressure ratio, which in turn increases the exit stagnation temperature. Therefore, the temperature change is increased, requiring more work to be inputted to the system. For my calculation problem, monoxide enters a converging, diverging nozzle with negligible velocity. The pressure is at 600 kPa and the temperature is at 300 Kelvin. Determine the critical properties in the nozzle. So what is known is that the temperature initial equals the temperature, which equals 300 Kelvin. The pressure initial equals pressure equals 600 kPa. So we need to find critical temperature, critical pressure, critical density, and critical velocity. Carbon monoxide is an ideal gas. It's steady one-dimensional flow and isentropic, and the Mach number is equal to 1. The properties we get from the tables are K equals 1.4. The gas constant is equal to 0.2968 kilojoules per kilogram Kelvin. And the temperature ratio is 0.8333. The pressure ratio is 0.5283. The density ratio is 0.6339. So we first solve it by finding the density, which is pressure initial over the gas constant times temperature initial, and we get 6.739 kilograms per meter cubed. For the critical temperature, we take the temperature ratio times temperature and get 250 K. Pressure, we take pressure ratio times pressure, which equals 317 kPa. For density, we take the density ratio times density, which equals 4.27 kilograms per meter cubed. For velocity, it's equal to the critical C, which is equal to the square root of Kr critical temperature. So we do the calculations there, adding a unit conversion of 1,000 meters squared per second squared over 1 kilojoule per kilogram, and we get 322 meters per second for the velocity critical.